Okay, welcome back guys. So in the first part of this lecture I described the general description of rotational motion and the circular motion and how they differ by each other and how angular motion can be used to explain the concepts in rotational motion. And in the second part of this series, in the second lecture of this series, I described about the angular equations of motion. Okay, now we are in the third part of this lecture, and in this lecture I'm going to introduce a new concept on you, which is the relationship between angular equations of motion and the rotational equations of motion, and the relationship between the angular vector quantities and the rotational vector quantities. Alright. Now, from the first part of this lecture, I have been describing the analogous situation between the translational motion and the rotational motion. So what lies behind this concept? Okay, let's find out. If I take an object like this, say an object which is going around a fixed point, as I have been describing, this is a fixed point, which is the center of the circle, and this is the positive x direction, the positive x-axis, positive, and take some point here like this. And call this as a theta, which is the position vector, the position angle, especially. Don't confuse the position vectors now, because it's somewhat complicated. Just think about the position angle, angular velocity, angular displacement, and angular acceleration. So this is angular position theta, and if the distance between these 2 points in this node, this is a circle. This is a circle. You know from 10 year, I don't know. It depends on the country you're studying. According to the geometry, I've seen that this is an arc. This is an arc. It's an arc. And if the distance between the x-axis and this arc is, I will name it as S. And if the distance is equal to R, you may know by now that S equals R theta. So you can derive it easily by taking this arc out of this circle. This is S, this is R. You can divide this into small parts, and you can take S equals approximately R sin theta. S1 equals R sin theta 1, S2 equals R sin theta 2, likewise Sn equals R sin theta n, so that the total for small angles sin theta 1 is approximately equal to theta 1, so S1 is approximately equal to R times theta 1, S2 is approximately equal to R times theta 2, likewise Sn is equal to approximately equal to R times theta n. So the summation of this is S1 plus S2 plus S3 plus likewise up to Sn is S, is approximately, we will take this as equal to R times theta 1 plus theta 2 plus theta 3 plus like that up to theta n is theta, so S is equal to R theta. So what you can take from this is S equals R theta. But what is S by theta? S by theta is equal to R, which is the radius. Radius of the circle and the radius of the motion. So you can say S equals, S is the angular, sorry, I will take it as translation displacement. We call it normal displacement, but distinguish I will take it as translational, right? Displacement divided by angular displacement is equal to r. So this is not only relevant for the displacement vector or the displacement, this is also relevant to any other equation of motion, any other vector quantity in translational motion and rotational motion and angular motion. So I write it as vector. So this is regarding vectors. So you can say this as vectors. You can take the distance between, it should be the displacement, because normally you take this displacement, but sometimes in some problems you may find the distance in some complicated problems. However, we have to take the displacement, not the distance. So vector quantity in translation divided by vector quantity in rotation is equal to. So this is a very important and generalized concept. It's very important to solve equations, and whenever you are not well versed with the subject, you can use this equation to understand the relationship between the translational motion and rotational motion. So I will derive the next quantity is using this concept. That's why this concept is useful, and you don't have to memorize this one, but it will be useful in some problems if you have the general concepts, the general equation and this equation in your mind, and use the next slide to do that, the derivation. So you know that vector in translational motion divided by vector in rotational motion is equal to. So I will take vector in translational motion. Now I will take the vector. I have already taken the vector of displacement to derive the relationship. Now I will take the vector quantity velocity. So vector in translational motion, velocity, the symbol is v, divided by the vector in rotational motion, the symbol is omega, is equal to. So this is equal to v equals r. So now I take the vector as acceleration, vector in translational motion for acceleration, and the symbol is a. Vector in rotational motion for acceleration, the symbol is alpha, which is equal to r, so a equals r. So this is a simple derivation from the generalized concept and the generalized equation we have derived. Using the equation we derived from the mathematical substitution for theta and getting the value for s and getting the relationship between s and theta. So you may wonder how this is true, because I just said that it is true for any vector. How this is true? Alright, so I will prove it. Take again this, motion, and this is the center, this is r, this is theta, right? This is theta f. Now the velocity of an object in rotational motion, the translational velocity is always perpendicular to the radius. So it's a tangential, we'll call that the tangential velocity because it's perpendicular. V, this is V, this is R. Right? Alright? So this omega, I'll draw it again because it's not tidy here, you can see properly. You can see properly. And draw this theta here, which is V. We call this one V1, right? V1 is V2 because it's an acceleration. I describe the equations of angular equations of motion in constant acceleration, so I'll take that the velocity, both the angular velocity and the tangential velocity or the translational velocity varies with time. Take the first one is V1, the second one is V2, and like this. So actually what happens is, this is V2, right, and this is V1. Right? The sum is given by, if you study geometry, you study the concepts, you know, the sum is given by, this is V2, this is V1, and this is delta V. The object is in this. So if this is theta, this should be equal to if this is theta, this is 90, this is 90, this is 90, this is equal to 180 minus theta. So that is this one. So this should be equal to, right? So this is at omega 1, this is at omega 2. So you can say this is the change in displacement, or the t transmitted varies with time in a similar pattern as the change in velocity varies with time with the change in angular velocity. And what's causing this motion to make happen with the distance r? So V2 minus V1 is proportional to omega 2 minus omega 1. To take the proportion, now I take V2 minus V1 equals r times omega 2 minus omega 1. This is delta V, I take it as V. Similarly, you can derive V equals r. So that's the analogy between the two quantities, V equals r omega and S equals r theta and A equals r alpha. And those are the relationships between the quantities in translational motion and the quantities in rotational motion. Alright. So the next concept and the final concept for this lecture is the period of motion and the frequency. Period of motion and frequency. Right. Now let's say we'll take the same circle. We'll take the fixed point of the center. Right. Now the angle displaced by this object while going around here, from here to here. Right? From here to here again. Right? Around this object like this is 2 phi. Call this as theta, t2 phi. Right? You know that omega equals theta by t. So I can write omega as 2 phi by t. Right? Omega equals 2 phi by t. I will take the total time. This is equal to t equal to 0. I will take this one as t equals t, capital T. So that omega equals 2 phi by capital T, which makes us t equals 2 phi by omega. Now the frequency of a rigid body going around in rotational motion, if I take it as f, is the number of cycles it makes around the center within a given unit of time. So, if there are 2 cycles within 1 second, I'll take a unit time. I take a unit time. If there are 2 rotations around this, or 2 number of paths taken, 2 number of displacements taken around this center, 300 degrees. This is 360 degrees. I'm talking. So this is 2 around the center. So the frequency is 2. So you know that F equals 1 upon T, the number of cycles per unit time. Right? F equals 1 upon T. If I substitute it here, 1 upon F. So I can write this as omega equals 2 times 1 upon T. So you know 1 upon T is F here, omega equals 2 pi F, or F equals omega by 2. So there are 2 important quantities that are described here, which are the frequency. So we got the relationships, omega equals 2 pi by T, omega equals 2 pi F, so this is WT. And you can, from this you can derive that T equals 2 pi by omega and F equals omega by 2. So in this lecture, we talked about the relationships between the quantities in translational motion and the relationships between quantities in rotational motion, and how they can be derived easily using the concepts we have learned so far, and also what affects the period of motion, what affects the time of revolution, that's the period of motion, and what's the frequency of motion, and how we can easily derive a simple relationship between the angular velocity and the period of motion, and the angular velocity and the frequency. In the next part of the lectures, I'll describe about the moment of inertia, the kinetic energy, and the other stuff which are relevant to the relevant motion. See you.